Well, good evening and welcome to the North Jersey Astronomical Group's February meeting. And we're going to start out with a talk about the James Webb Space Telescope, which I'll be presenting. And following the presentation, members, if you want to stick around, we'll have a business meeting and we'll take it from there. Excuse me. So tonight, I'm going to talk about the Webb Space Telescope, which is one of the biggest projects in astronomy in recent years. It's taken 17 years, more than 17 years, to build and launch this telescope, along with numerous delays along the way. Was a major redesign in 2005. There were technical glitches along the way, and there were even problems with the launcher as well. So I'm going to talk a little bit about the telescope and what its current status is and what its mission is as well. So the Webb Space Telescope is often thought of as a successor to the Hubble Space Telescope, which is one of the most successful telescopes in history. But the Hubble Space Telescope started out, it was launched in 1990. We had launched space observatories before that in the late 60s and 70s, but really the golden age of space telescopes started with the launch of the Hubble Space Telescope in 1990. And it was not alone, though. It was part of a larger program that was called the Great Observatories. And so you had the Hubble Space Telescope launched in 1990. It was joined by the Chandra X-ray telescope, the Spitzer infrared telescope, and the Compton Gamma Ray Observatory as well. And so all four telescopes were operating and looking at the universe at these different wavelengths. And that was really kind of the goal, this kind of multi-spectral view of the universe, in some cases simultaneously observing objects at different wavelengths. And so really quite exciting. Of those four observatories, two of them are still operating. The Hubble Space Telescope and Chandra are still operating after all these years. Now, as you may have heard over the past year, the Hubble Space Telescope is getting long in the tooth. It's been in space for 32 years at this point. And so it shut down a couple of times last year, twice. It was shut down due to various technical problems, and fortunately, NASA was able to switch to backup systems and get the telescope back up and running. And it is back up and running and is operating, and hopefully will operate for a few more years at least. And so now comes the James Webb Space Telescope. And it will be a successor to the Hubble, but it'll be quite different than the Hubble Space Telescope. It's a different type of instrument, and so we'll talk about that during this talk. It is primarily an infrared telescope, and it will be imaging it won't be imaging in the visible. It will be doing all of its work in the infrared. And hopefully by the end of this talk, it'll be clear as to why that is, why it's so important to this mission. And so let's talk a little bit about the science, the mission that it is going on here. It has various aspects. Of course, the telescope is used for many things, but primarily what we want to do with this telescope is we want to explore the early universe. We'd like to know more about the early history of the universe. We, of course, want to, as part of that, want to look at galaxies. We'd like to know more about distant galaxies, especially the early history of galaxies. We'd like to know a little bit more about how they formed and how they have evolved and changed over the billions of years since. And, you know, over the past 100 years, we've learned quite a lot about galaxies. We'd really like to know more. Stars, of course, we've been looking at stars in the nighttime sky, and it's one of the most prominent things about the universe. When we look out at the nighttime sky, we see these stars. We've been looking at them for thousands of years. And we'd really like to know more about them. And we'd also like to know more about how these stars form as well. And speaking of stars, there are planets orbiting around some of those stars. And so we'd like to know more about exoplanets. We've been discovering all kinds of exoplanets over the past several years, and we've been fascinating for a very long time about worlds orbiting other stars and whether or not those planets might have life. It's a fascinating topic. We'd love to know whether or not there are Earth-like planets out there, and hopefully the James Webb Telescope will help us answer some of those questions. And so I have a little short little video here that kind of explains or gives an overview of the whole mission.
Under construction is the premier telescope of the next decade. A next-generation space telescope designed to cause yet another giant leap forward in our understanding of the cosmos. It will carry some of the most advanced technologies ever placed on an orbiting observatory.
18 articulated mirror segments, 2.75 times the diameter of Hubble's primary mirror. Microshutters, wavefront sensing and control subsystem, 12 by 18 meter, 5-layer Kapton-based sunshield.
The Webb telescope, a revolutionary tool able to study every phase in the history of our universe.
The Webb telescope.
And so there's the overview of the telescope. And when we say that the telescope is an infrared telescope, well, what does that mean? Usually, I think a lot of people don't think of heat as being light, but that's what it is. It's infrared light is really kind of heat. And the Hubble Space Telescope has a fairly broad range. It can obviously image in the visible. It can image a little bit into the infrared and a little bit into the ultraviolet, but that's about it. There are these other wavelengths that are also very interesting to us, and Webb will be looking at the infrared part of the spectrum here, the near and the mid-infrared bands of the infrared. The Spitzer Space Telescope, which is no longer operating, was looking at the longer wavelength infrared, but James Webb will focus on this part of the spectrum. And so what's different about the James Webb Space Telescope? Well, it's much bigger. You've got a mirror that is 6.5 meters across. The Hubble Space Telescope, a lot of people are surprised. It's actually not a very big telescope. It's 2.4 meters, or roughly about 95 inches in diameter, which is not really that big compared to some of the telescopes here on the ground. But why is that? Well, remember that we had to get the Hubble Space Telescope up into space, and our primary vehicle at the time was the Hubble Space Telescope. The space shuttle that was carrying the Hubble Space Telescope up into space. And the shuttle bay is only so wide. You can only fit so large of an instrument inside that shuttle bay. And so that determined the size of the Hubble Space Telescope was the size of the shuttle. This telescope is 6.5 meters, which is 21 feet across, or about 255 inches. And that means that it collects about 7 times as much light as the Hubble Space Telescope. In terms of the size of the overall spacecraft, it's about 70 feet long. about 46 feet wide, or in other words, about the size of a tennis court. So it's fairly large. At least the sun shield on this spacecraft is fairly large. And so this is a very large observatory. And the problem is, well, how do you get something this big into space? Because we do not have rockets that can fit something that's 70 feet long and 46 feet wide into it, inside of it. And so what you have to do is you have to make the spacecraft fold up. And so you got to fold it up kind of like origami and stuff it inside of a rocket and shoot it off and then have it unfold. And so that's exactly what they did. And one of the reasons why it's taken so long for this mission to get off the ground, because it's a very complicated process to create something like this. So, so this is how the spacecraft was folded up inside, and that's how the rocket was chosen. The biggest rocket that was available at the time that the telescope was being designed was the Ariane 5 from the European Space Agency. And so that's why this was chosen. It had a big enough nose cone area to be able to contain this spacecraft. And so that's how that was chosen. If we take a closer look at the optics here of the telescope, here you can see it getting ready for testing. The Webb Space Telescope is an anti-stigmat design, which is a very special design that is meant to eliminate the errors or aberrations that usually occur in reflecting telescopes. And so, so this is a three mirror design. You have, of course, the large primary mirror, which is concave in shape. The secondary mirror, which you can't really see, but it's right at the top here. That's a convex mirror. And then there's another mirror down in the bottom here as well. And so this is a three mirror design that gives you a nice flat field for your instruments, also gives you a fairly wide field as well that's free of some of these aberrations. And so it's a very nice design. If we take a closer look at the primary mirror here, this is not a glass mirror. Usually when you think of telescopes, you think of a glass mirror inside of it, but this is not glass. This is a lightweight metal called beryllium. And beryllium is, it's strong, but it's lightweight. It holds its shape over a wide variety of temperatures, and so is the perfect material for this. You'll notice that the surface of the mirror is also coated in gold. That's not just for show. Gold is a really good reflector of infrared light, and so that's what they used to coat these segments here. And you'll notice that, yeah, it is not a solid mirror. It's made up of all these little hexagon shapes here, these little segments that all work together to form one large surface. And if we look at a closer look, here's a model of the mirror segment. The backside of each mirror segment looks like this. There's 18 of them. There's 18 hexagons. They're about 1.3 meters across. And they have very small motors on the back of it. And those motors help align the telescope. They help also shape it as well. And they can very accurately position the segments to within about 10 nanometers, which is 10 millionths of a millimeter. So it's pretty amazing, very precise system here for aligning and putting the mirrors in the right place to create some great images. And so we've got these 18 mirrors that all work together. And as mentioned, it's got a fold. The fairing on the Ariane rocket is only about 15 feet wide. And so you've got to make this mirror fold up. And so that's what they're showing here. You can see that the one side is folded back. This one is folded forward in place. And so those, when it was packed up to be launched, were folded back and then eventually put back into place once the telescope was in space. So pretty amazing process here. And so where is the Webb Space Telescope? Well, it's not in Earth orbit the way that the Hubble Space Telescope is. It is orbiting a spot that's beyond the orbit of the moon called L2. These points, these 5 points that you see around the orbit of the Earth are Lagrangian points. They're spots where the gravity of the sun and the Earth kind of balance out. And they make great spots for spacecraft. It gives them a relatively stable place for the spacecraft to be, minimal fuel use, and L2, where it's sitting, is almost 1 million miles away from the Earth. And it's not just sitting there, it's in this little, I shouldn't call it little, but it's actually pretty big. You have this halo orbit. You have this little orbit, it's going around and around it's orbiting around the L2 point in this halo orbit. And the halo orbit is about the size of the moon or so. And so that's where this telescope is orbiting along with the Earth. And so good lines of communications there. It keeps the spacecraft away from the heat of the Earth and Moon. And that's very important. You've got to keep an infrared telescope, has to be kept cool. If you're going to look at these very faint infrared signals from the distant universe, you can't have your telescope heating up and interfering with those observations. And so you got to keep it cool. And so this is the sun shield being tested out. The sun shield, as mentioned, is really quite large. It's made of 5 layers of kapton. It's kind of like a mylar type material. It's aluminized, and it keeps the telescope at a temperature of 50 degrees Kelvin, which is about 370 degrees below zero in the Fahrenheit scale. And so how does this get deployed? And so we have another little video here that shows you how this all came about.
The James Webb Space Telescope is the largest space telescope ever built. Its tennis court-sized sun shield, along with its 21-foot 3-inch primary mirror, will enable Webb's instruments to see back in time to when the first stars and galaxies formed after the Big Bang, more than 13 billion years ago. But Webb's size is too big to fit into any existing rocket, so it's designed to be folded like origami, so it fits inside the almost 15-foot wide payload fairing of the very powerful Ariane 5 rocket. Once in space, the Webb telescope is slowly unfolded in a well-choreographed series of deployments. The solar panel is deployed first to provide power. About 12 hours after liftoff, Webb's thrusters are fired in what's called a mid-course correction burn to fine-tune Webb's trajectory. About 24 hours after liftoff, Webb's high-gain antenna is deployed, enabling communication with ground controllers. Webb is traveling so fast, it passes the moon in about 2 days. Here, a second mid-course correction burn sets the spacecraft on course toward its orbital destination. On day 3, special pallets holding Webb's folded sun shield deploy. First the forward pallet, then the aft pallet. Webb's central tower is extended, lifting Webb's telescope and instrument package to its operational location. Webb's momentum flap is deployed. As the sun's solar pressure pushes against Webb's large sun shield, this flap helps stabilize the telescope. Special covers hold Webb's tennis court-sized sun shield in place during launch. These covers are now released.
That's weird.
Freeing the sun shield for deployment. The first of Webb's sun shield mid-booms deploys, unfolding and extending one side of the 5-layer kapton sun shield. Then, the second sun shield mid-boom deploys. Once both booms are fully deployed, the center rim is deployed, and the sun shield is slowly tensioned. This separates the 5 layers. On the sun-facing side of the telescope, a radiator shade deploys to protect Webb's spacecraft systems from the sun's heat reflected off the sun shield. Near the 10-day mark, the MIRI instrument's cryocooler is started. It begins lowering the MIRI instrument's temperature to about 6 degrees above absolute zero. Controllers now begin the process of deploying Webb's optics. Webb's secondary mirror deploys first. Then, an additional radiator panel behind the telescope deploys. This helps remove more heat from the spacecraft. About 12 days after launch, the first wing of the primary mirror is rotated into place. A few days later, the other mirror wing is rotated into place. About 30 days after launch, another mid-course correction burn further tunes Webb's course toward its final operational orbit, about 1 million miles away from Earth. For the next several months, optics engineers using Webb's NIRCam instrument will align and focus Webb's 18 primary mirror segments into a perfect monolithic mirror. It will take about 6 months before Webb is fully ready to capture its first science image.
And so there you have it. This is the process that has been taking place over the past few weeks. And all these deployments were taking place as the spacecraft traveled out to the L2 point beyond the moon. And everything went pretty well as far as we can tell. And things went pretty well, and it arrived at the end of last month, arrived at its halo orbit at L2. And so a complicated process, but everything seemed to go pretty much flawlessly. So that's really quite amazing. A lot of astronomers were on the edge of their seats during this process. I'm sure people have spent quite a number of years working on this, and would have been a shame if it didn't quite work out the way they hoped. But the instruments, a couple of which are mentioned in that video, these are the 4 main instruments for the spacecraft. You've got the near-infrared camera, or NIRCam, the near-infrared spectrograph, or NIRSpec, the mid-infrared instrument, or MIRI, and then the near-infrared imager and spectrograph, or NIRIS is an acronym. NASA loves its acronyms. And so this is where these instruments are going to be observing in the near-infrared and mid-infrared. NIRCam is an instrument that will be used to detect light from the earliest stars and galaxies. We'll look at stars in nearby galaxies, young stars in the Milky Way. It'll look for exoplanets and Kuiper Belt objects in our own solar system as well. The NIRSpec instrument is designed as a very nice design where it can observe 100 galaxies all at once simultaneously, which is a real advance. Instead of observing them one at a time, you can do it 100 at a time, which is pretty cool. MIRI is the mid-infrared instrument that's observing at longer wavelengths than the other instruments, and it's a wide field camera as well as a spectrograph. And so it will capture the redshifted light from distant galaxies. It will look at newly forming stars. It can look at faint comets, and as well as objects in the Kuiper Belt as well. And the NIRIS instrument, that will be used for first light detection. We'll talk about that in a moment. We want to look at the earliest light in the universe. It'll be used for exoplanet detection, and also for looking at the properties of exoplanets as well. So a nice battery there of infrared instruments. Now, you may be familiar with this particular image from the Hubble Space Telescope. This is one of the deep fields, so-called deep fields, where they took the telescope and pointed at a relatively blank area of the sky and just exposed, and took exposure after exposure, trying to record just as much as possible and record the faintest objects that are possible. And when you look at this image, there's a couple of foreground stars you can see here a couple of bright ones there, a couple of bright stars, but everything else that you see is a galaxy. So this image contains approximately 15,000 galaxies. The Hubble Space Telescope has been able to image objects that are about 500 million years after the Big Bang. But it can't really go much further than that. The James Webb Space Telescope, being a larger instrument, can view objects that are up to 100 times fainter than what the Hubble can see. And so hopefully the Webb telescope will be able to do much better than Hubble in this regard. And so how does that work? It's really kind of a very fortunate thing that light does not travel infinitely fast. It travels pretty quickly, 300,000 kilometers per second. But it takes time for light to reach us from billions of light years away. And that's a fortunate thing because it actually kind of lets us look back in time. We can look the further out we look, the further back in time that we're looking. So that's what sometimes people call it, why people call it look back time or cosmic time, because we can look back into the past. It's almost like having a time machine available to you. Not quite as good as that, but still it's pretty good. And so as I mentioned, the Hubble Space Telescope has been able to look pretty far back, more than 13 billion light years into the universe and 13 billion years into the past. But really the big mission for the James Webb Space Telescope is to look back as far as possible and see that first light, the first light in the universe, which is kind of seems to be a bit of a paradox, that the early universe would have been dark, but that's really the case. If you go to a time period before about 300,000 years before, after the Big Bang, I should say, the universe was just the soup of quarks and stuff and energy, and photons couldn't travel really. They just were immediately absorbed, and so light couldn't really travel in the early universe, and so it's really kind of dark. Lots of energy, but very dark. It wasn't until about 300,000 years later that the universe cooled off enough that ordinary atoms could form and light could travel long enough distances. And so we'd like to see that first light. It'd be really quite amazing. And hopefully we can learn a lot about the very early part of the universe. Speaking of the early part of the universe, we'd also like to look at the very early galaxies that are located out there. And the light that is coming from those galaxies is what we call redshifted. The universe is expanding over time. And so as the light comes towards us, it's kind of stretched out by the expansion of space. And that shifts the light down into the infrared part of the spectrum. And so if we want to look at those very early galaxies, we got to have an infrared telescope in order to look at them. So let's move forward here to speaking of galaxies. Of course, as I mentioned, we really would like to know more about these galaxies. They're really fascinating objects. We've got stars and gas and dust in these galaxies, and I'd like to know more about, as I mentioned, about how they change over time. There are, of course, different kinds of galaxies out there. We usually think of galaxies as being spirals because that's what the Milky Way is. So we have an example of a spiral galaxy, but there are also these very large elliptical galaxies as well. And we've got irregular galaxies here too. So you get a wide variety of different shapes of galaxies here, and we'd like to know more about them. We know that galaxies collide over time, and it's a big part of the formation process of galaxies. Our own Milky Way is the result of many such collisions over time, and so we'd like to know a lot more about that. And speaking of galaxies, With the Hubble Space Telescope, we've discovered that a lot of these galaxies, even maybe even most of galaxies, have these supermassive black holes down at the core. And so we'd like to examine those. Problem with looking at cores of galaxies is that there's a lot of gas and dust there. And so if you want to see that sort of thing, you got to have, you got to look at the infrared light that's coming from there, because the infrared light will, because the wavelength is so large, it'll pass through that dust and gas and gives you a better view of those areas. And so that's another bit on our list of things to do with the James Webb Space Telescope. We'd also like to know more about dark matter. It's really kind of a little bit embarrassing. When we look at all the matter in the universe, we kind of put it in one big lump. The ordinary matter we think of, like stars and galaxies and dust and gas, that makes up only about 20% of the matter in the universe. The rest of it is dark matter. And, well, what is it? Well, we don't know. We'd really like to know more about that. It could be some kind of particle that we haven't discovered yet. It certainly is stuff that doesn't interact with ordinary matter, and so it's very hard substance to study. But the James Webb Space Telescope should be able to help us map this dark matter. Even though dark matter can't be seen, it's kind of invisible to us, we can see its effects on the motions of galaxies and how galaxies move and rotate and that sort of thing. And so we can kind of create maps of these things with these telescopes. And so hopefully the Webb will be able to help us out with some of that. And of course, we're interested in the Milky Way. We would like to look at more of the Milky Way. The dust and gas that's in our Milky Way looks pretty up close, and we can look at them with our telescopes, the nice nebulas that we see. But some of that gas and dust blocks our view of part of our Milky Way. We'd like to be able to peer through some of that dust and gas and get a closer look at some of these other areas of the Milky Way. And as mentioned, we've been fascinated with stars for thousands of years. We've been looking up into the sky and seeing these beautiful stars. But we'd really like to know more about where these stars came from, And so, excuse me. So we'd like to examine stars up close, and certainly the Hubble Space Telescope has made great strides in that regard. This is a very famous image. You'll recognize the famous pillars of creation located in Eagle Nebula. And so inside these pillars are young stars that are being born. But the dust here and the gas is hiding those stars from us. If we use infrared, we can get a little bit better view of that. The various projects, including the Hubble Space Telescope, that have been looking at the Orion Nebula. You'll recognize the Orion Nebula in the background here, one of the most photographed objects in the nighttime sky, and of course it's visible right now. And we've discovered this in this nebula, which is about 1,300 light years away from us. It's home to about 150 baby stars. They're very young stars being born here. Little clumps of gas that are hiding baby stars. And we'd like to look inside some of those little bubbles there and take a closer look at what these young stars look like. So here's an example. On the left-hand side, you've got a Hubble Space Telescope image, and on the right, you've got an infrared view. I assume this is the Spitzer Space Telescope. The image on the left from the Hubble probably contains a little bit of ultraviolet light as well as visible in infrared, but the Spitzer there is definitely in the infrared there. So this gives you an idea of what the Webb Space Telescope images might look like. This also, I believe, is a Spitzer Space Telescope image. I think this is the Eta Carina Nebula in the southern hemisphere. And so this gives you an idea of what this might look like from the new Webb Space Telescope. And as mentioned, exoplanets is a really hot topic in astronomy. We've been discovering tons and tons of objects orbiting around nearby stars. At this point, this morning I checked NASA's website, and the count of objects that have been discovered at this point is at 8,460. So there's almost 9,000 objects out there that we've discovered. About 5,000 of them have been confirmed as being planets orbiting these other stars. And so that's pretty amazing. And, these young stars that we're studying, we would like to study, well, that goes hand in hand with our exoplanet research, because we'd really like to know how solar systems are formed, how are planets formed. And as I mentioned, the young stars are kind of shrouded in these clouds of gas and dust, and so it makes it very difficult to study young planets. And so the infrared light will help us with that aspect too. And as you can see, it seems that these galaxies are forming disks. These are accretion disks around these young stars, and we'd like to study those disks up even more closely than we have in the past, and learn how they create planets. Now, of those thousands of planets that we've discovered, there's about 6 or so that are considered potentially habitable exoplanets. And by habitable, we don't necessarily mean that they're Earth-like. It's just that they are at a proper distance from their star that they're located in a position where liquid water could exist. And we use that as a criteria. We know that all life on Earth requires water, and so that's a good place for us to look for life elsewhere in the universe, is look for planets that have liquid water on the surface. Not the only possibility, but it's a good place to start looking. And so there's about 6 of them. You can see a few of them listed and their distances from the Earth or from the sun. And so there's quite a lot of these floating around there. Out there in space, and we're discovering more all the time. And hopefully the Webb Space Telescope will help us learn even more about these objects. And we get asked that question all the time. A lot of people will ask us, well, what about this planet? What about that exoplanet? What's it like? And in some cases, we really don't know. We can only guess in some cases. We have limited information about some of these worlds, and hopefully the James Webb Telescope will be big enough and have the right instruments to be able to tell us more. And so we mentioned the spectrographs earlier, and so well, how do these spectroscopes work? And well, basically you have the light coming in through the telescope. It's sent to the instrument. It usually passes through a slit, though I think one of the instruments at the Webb Space Telescope operates without a slit. But anyway, the light is broken up by a diffraction grating, and the light is spread out, and you can get a nice spectrum from it. And those spectrums are like fingerprints, and they can tell you what the material is made of that's emitting that light or reflecting that light. And so they're incredibly useful devices. We can not only tell what chemicals they're made of, we can tell how fast objects are moving with them and that sort of thing. And so very powerful pieces of equipment that we can use to learn more information about these objects. Not too long ago, there was a big announcement, big discovery. This is an exoplanet just simply called K2-18b, and it's located about 124 light years away from us. And it's a super Earth. In other words, it's about 8 times larger, 8 times more massive than the Earth. And so it's kind of a supersized Earth. And astronomers use a spectroscope and were able to detect water vapor in the atmosphere of this planet. and it is in the habitable zone of its star. It's not really an Earth-like planet, but it is really very interesting that we're starting to be able to tell what these atmospheres are like. And just a couple of weeks ago, I think it was only about 2 weeks or maybe 3 weeks ago now, they discovered another planet that's a bit bigger than Neptune. It's orbiting a red dwarf star about 150 light years away. And it also seems to have water vapor in its atmosphere. So another planet that has water vapor in its atmosphere is really kind of interesting. So new discoveries coming all the time, and the Webb Space Telescope will help us discover even more, I would think. Another area of research that the Webb Space Telescope will be engaged in is looking at brown dwarfs. Brown dwarfs are really odd objects. They're about 70 times more massive than a gas giant planet like Jupiter. But yet they're not really big enough to become full-fledged stars. So they're odd little objects that are too big to be planets, but not big enough to be stars. And so they're kind of failed stars. And since they're very cool and dim compared to a star, they're very difficult to see. And so that's what the Webb Space Telescope can help us with. We'd like to find the lowest mass brown dwarfs. We'd like to look at the smallest ones and try to figure out what's the dividing line between a planet and a brown dwarf, and what's the dividing line between a brown dwarf and a low mass star. We'd really like to know a lot more about that. These are very interesting, unusual objects, and there are quite a lot of them out there. Now, in order to look at exoplanets, one of the instruments, I think it's NIRCam, is equipped with a coronagraph. And so what's a coronagraph? Well, coronagraph basically creates eclipses. And so here's a little image of the 2017 eclipse. And the coronagraph has something inside of it that is used just to block the light of a star. And once you block the light, usually the planets that are orbiting a star are overwhelmed by the light coming out of it. But if you cover it up, you get to see those planets, and you can discover more exoplanets that way. So the NIRCam is equipped with one of these coronagraphs. And so that can help us find more exoplanets and perhaps more of these brown dwarfs orbiting around other stars. And so the Ariane 5, here it is on the launch pad in December of last year. It was launched from French Guiana, and it was really quite a spectacular launch. Lifted off on December 25th on Christmas Day. It lifted off successfully, and it was really a spectacular launch. And NASA described it as perfect, as kind of a flawless launch. And that was really great news because the launch was so well done by the European Space Agency. They used minimal fuel to get the spacecraft to where it had to go. And so that means that it's got a good fuel reserve. And so they estimated that the telescope should have at least 10 years worth of fuel, maybe even 20. And so that's great news for this spacecraft, because it was very expensive to build. We're talking about almost a $10 billion project. And so it'd be nice to get some real mileage out of this thing. And it looks like, hopefully, if everything goes well, we will have a very long-lived spacecraft out there beyond the orbit of the moon. And so there is a little overview of the James Webb Space Telescope. It's in its halo orbit. And just last week, maybe less than a week ago, light was sent through the telescope, bounced off the mirrors and went into the NIRCam. And the engineers started the process to align the mirrors, and eventually they'll start testing the instruments. And that's going to take a while. I know a lot of people are kind of wondering, well, when are we going to see the first images? Well, it's going to be a while yet before they get everything lined up and tested out. We might see some early test images perhaps, but I would not really expect anything until about the end of June, early July is the timeline that they originally put out for this. And so all this time will be spent aligning the mirrors and testing things out, make sure everything works. And then finally the science can begin at the beginning of the summer, and stuff will start flowing down from the spacecraft at that point. So a very exciting time to be interested in astronomy. This is going to be, I think, going to be a groundbreaking telescope, expanding on the previous space telescopes. And by the way, what about the future? Well, Hubble Space Telescope hopefully will continue to operate, and will operate in parallel for a couple of years at least with the James Webb Space Telescope. But what about the future? Well, eventually we'll have another space telescope flying in space as well. This is the Nancy Grace Roman Space Telescope, which is also an infrared telescope. And it's almost an exact duplicate of the Hubble Space Telescope. The mirror is exactly the same size. This is a surplus, I believe, started out as a surplus telescope. It was originally meant to be some kind of spy satellite, and it never got used, and it was turned over to NASA, and they turned it into this wide field infrared telescope. And it was very nice that they named it after Nancy Grace Roman. If you don't know her name, she was the first chief astronomer of NASA, and she shepherded a lot of spacecraft into orbit, including the Hubble Space Telescope. Sometimes people call her the mother of the Hubble Space Telescope. So it's nice this spacecraft was named after her. I believe the launch date has been delayed. Originally, it was supposed to fly in 2025. Looks like 2027, the spring of 2027, this will fly as well and operates in parallel with the James Webb Space Telescope. The difference being this is a very much more wider field of view than the Webb Space Telescope, and so it will complement the science being done by the James Webb Space Telescope. So there you have it, a little overview of this space telescope, and so we hope you enjoyed that. I know we've got a couple of questions in the chat here, so let's go back and
Kevin,
look at those. Yes, yeah.
Do you want me to read them off to you?
Well, sure, yeah. It'd be easier that way, I think.
Okay, so Jeff Carlisle asks, when the talk is over, what can James Webb do that Spitzer cannot?
Well, certainly it's observing in a different wavelength. Spitzer tend to concentrate on the longer wavelength infrared, and so it had a different focus to its science missions. But certainly it's much bigger. I can't remember off the top of my head how big the Spitzer Space Telescope was, but not nearly as large as the Webb Space Telescope. So Webb is much larger and able to see much further out in the universe than either Hubble or Spitzer could.
Thank you.
John Mickitz asks, also would planets in the solar system by objects of study?
Yeah, they certainly one area, as I mentioned, would be Kuiper belt objects, because they're so faint and so dim. They are really only kind of glowing in the infrared. And so if we want to find some more Kuiper belt objects, and also Planet 9, that's undergoing at this point now too. We're looking for, there are some astronomers who have looked at the orbits of comets and suspected that there might be another relatively large planet in the outer solar system that we haven't found yet, which would be really amazing if we could find something like that. And so certainly, the Webb Space Telescope will help us search for these dim objects, dim icy objects at the edge of the solar system. Certainly, that's the case as well. I don't know if they really have any plans for using Webb to observe the major planets. I don't know if they could. If in some cases it might overwhelm some of the more sensitive instruments, but off the top of my head, I'm not sure. That's an interesting question. I'd have to look.
You think it could penetrate let's say the atmosphere of Jupiter through the gas?
Some of it, but not
too far.
Not too far. Yeah. It wouldn't be able to see too deep, I would think. But yeah. certainly would be interesting to see if they actually look at the major planets as well.
The next one is for me, but I think you partially answered it before. Like, how far back can James Webb see, or at least how far back can we hope to see with James Webb? Can it make it back to the cosmic microwave background? I know that's the wrong wavelength, but how far can it get close to that?
Right. You can't see the cosmic background radiation. That's all microwave. Redshift is so much that it's often in the microwave, well beyond the infrared, and so that wouldn't be able to. Webb would not be able to detect that. But yeah, certainly within a billion years of the Big Bang, but perhaps a little bit more than that. Your limitation is the 370,000 years is when the universe first became kind of transparent, and that's where the cosmic background radiation comes from, and so that's your real limit. But yeah, hopefully we'll be able to see the very first stars and the very first galaxies could be viewed, and we know that those were forming within the first billion years after the Big Bang. So we'll see how far it goes.
Cool. The next one is again from John. Suppose there's an idea of the resolution of this instrument for various distances. Likewise, I suppose the instrument output might be upgradable with software.
Well, certainly that's always the case. If you come up with new techniques, you can always upgrade the software of the telescope. That's for sure. But its resolution is kind of fixed at this point. Unfortunately, unlike the Hubble Space Telescope, the Webb Space Telescope can't be serviced. It's too far. It's almost 1 million miles away, and so it really can't be serviced the way that Hubble was able to be. And actually, Hubble was designed for that. It was designed to be modular. You could go up and you could pull out an instrument and replace it. And that happened a couple of times. I think the latest one was the Wide Field Camera 3, and they kept replacing it with higher and higher resolutions. The equipment itself, the hardware itself, was being replaced. So that's obviously not possible with the James Webb Space Telescope. So that's a limitation there. But certainly, yeah, they could upgrade software if someone comes up with a new technique or something. Certainly, that could be done.
Okay, next one's from Terrence Baz. Could you speak more about the third mirror that you referred to? I had imagined that the light from the secondary mirror would go through a lens to the imager or the camera. I really couldn't because I tried to look up more information about the curves on those mirrors, and apparently it's very complex, these anastigmats, in terms of their curvatures and that sort of thing. It's very highly kind of computerized design, so to speak, and so it's not simple curves that are on this. On the optics for this telescope, because and you can kind of see it if you look at images of the telescope, that the secondary mirror is not exactly centered. It's slightly offset. It's slightly off axis, and so it has this weird design where it's a little off axis, and so I'm not quite sure what shape that third mirror is. I tried to look it up and I could not find any information about that. But certainly the primary mirror is concave, as you might expect, but the secondary is some kind of convex shape of some kind that corrects some of these aberrations that we ordinarily see in our own telescope, our own backyard telescopes have some of these aberrations, and this design virtually eliminates some of those. Hey, Cliff, do you know off the hand?
Yeah, it's a member of a family of telescopes called three-mirror anastigmats.
Right.
And Vera Rubin is one of these also.
Right.
And the simplest form of this is the Baker-Paul. Imagine you've got a big paraboloid that's going to have a big, fast paraboloid that has a lot of coma in it. If you put a convex spherical mirror as a secondary and a concave spherical mirror of the same radius as that convex one in between the primary and that, of course, it's going to obstruct a lot of light. The interesting thing you get is a focus which has the same focal ratio as the primary paraboloid, but coma is gone. It's an amazing kind of an optic. And both the James Webb and the Vera Rubin are pushing that design to opposite extremes. I mean, the Vera Rubin has the tertiary and the primary actually ground into the same blank, but it's the tertiary is concave, at a different radius from the primary.
Right. Okay.
And this one is complicated because of the tilts, but there's probably some funny toroidal things ground into them besides the simple conic sections that are at Vera Rubin telescope.
Right. Yeah. Yeah. I know. When I looked at the primary mirror, they have the segments are separated into like 3 different zones, and those are very precisely, I mentioned, they're very precisely controlled as to where their position is going to be, and they do their final alignment. So,
well, one of the things they're busy doing right now, or later in the process that they're doing right now, is besides just getting all of those images to line up on top of one another, they're doing minute changes in the radius of curvature of those mirrors to get those individual images all in phase. So it really acts like a monster single mirror.
Yeah, it's kind of amazing how they can change also change the curvature of the shape of the mirror itself, each segment. It's pretty cool too. Yeah, pretty amazing. Thank you, Cliff.
Thanks, Cliff. Yeah, that's a great explanation. Next question is, perhaps within 10 and 20 years, when it gets near the end of its service life, will we have the technology to go and refuel the telescope? Like, for instance, did they put a mid-air refueling valve there?
They did not.
They did not.
The last servicing mission for the Hubble, they did put a docking mechanism on the back of it, for figuring that, well, maybe just in case, if they wanted to have better control over the reentry once the telescope has reached the end of its life, that they could technically send up something robotic to dock with it and control its reentry in some way. So, but they did not do that with James Webb. I guess they kind of figure that like 20 years from now, the technology is going to be so out of date, they'll probably want a whole new telescope at that point,
Yeah.
So,
next one's from Dave Brody. I think he's a writer or editor for space.com, if memory serves. He's also an NJAG member. Yeah. Sharing with the group, I just made this video about using the James Webb Space Telescope for exoplanet detection and what types of stars can host Earth-like worlds. Planet hunting with the James Webb Space Telescope, and there's a YouTube link. Dave, if you're still there, could you also send that link to the club's email IO group? That'd be great. We'd appreciate that.
I will absolutely do so.
Great.
Yeah, thank you. I got one from Al Karsich. What exactly is the mass holding of the James Webb Space Telescope in the halo orbit?
Well, I mean, it's orbiting just the way that a satellite would orbit around the moon or the Earth or something like that, But yeah, I guess it is sort of odd when you think about it, because usually I think of a satellite orbiting around a mass in the center, but it isn't really doing that. But I guess it's just sort of orbiting around this balance point, that between the Earth and the Sun, and you're just able to. It's a fairly stable point, and so you can just kind of orbit around that.
May I clarify my question?
Sure.
I understand it's orbiting around the sun along with the Earth at the Lagrangian point. Yeah. But every depiction I've seen, it's not only orbiting around the sun, it's also orbiting around an invisible point in space. There's no mass there.
Yeah,
What is
no.
holding it in that orbit is my question.
Cliff, you have a better answer? Go ahead.
It's very much like imagine two stars, a binary system, orbiting each other. They're both orbiting the balance point between them.
Yeah,
And
it's
there's
true.
nothing there.
Yep.
It's very much like that.
Yeah.
That's a balance point between the gravity of the sun and the earth, and it's orbiting that balance point.
Sure. Good point. Thank you.
Thank you.
Okay.
That's it in chat. Is there any other questions for Kevin?
I got a comment from a chemist.
Okay. Go ahead.
Everybody talks about looking for water as though water is this amazingly scarce material. It turns out that the most abundant atom in the universe is hydrogen. And the most abundant atom that can react with hydrogen is oxygen. So you could just figure statistically the most abundant molecule in the whole universe has got to be water. So there's going to be water everywhere. We may not have seen it too much. I mean, we've got moons in the solar system that are mostly water.
Yeah, chock full of it.
Yeah, it's going to be there. And I bet they're going to be bugs too.
Sure. Okay.
Cliff?
Okay. Thank you for everyone. Hope you enjoyed that, and we'll move on. So thanks for joining us. Mary Lou, what are we doing for our speaker for the next meeting? We should mention that for the March meeting. Again, we'll be on a Tuesday, second Tuesday of the month at 7:30 p.m. We're trying out this new time slot. And so what's coming up next, Mary Lou?
Okay, so the next month, so March 8th, Mark Sidarsky is going to tell us about the Adirondack Astronomy Retreat, best star party ever. And we all have to sign up to go to this star party up near the top of Lake Champlain on the New York side, not the Vermont side. So it sounds exciting. If we ever go back to having in-person meetings at Montclair State, we will be in a new room, Richardson 201, back in Richardson Hall, because the room we used to have is signed up for Tuesday nights at this time. So we can't have that room. So we could have this other one. So yeah, that ought to be nice.
Okay. Good. Thank you.
By the way, there's the James Webb Space Telescope as seen from my observatory.
Oh, that's right, Cliff. I forgot about that. You actually took that picture. There it is.
See that glint right there where it got to 15th magnitude? That's just a tilt of the slightly wrinkled sunshade. And the last set of trails I got, it's rock solid, constant 18th magnitude. And I think that means they got their gyro stabilized and they're looking at that HD star and the Great Dipper for doing their alignment. It's probably not going to change in brightness very much. But I'm going to skip out on your business meeting. Bye.
Okay. Thanks, Cliff. Yeah.
Thanks for the info, Cliff.
Bye.
Thanks, Cliff.
Night.